Thank you for coming, everyone. My name is Myungsoo from Youngsan University in South Korea. I'm going to present my research work, which is optimization of a woven fabric composite structure for improvement of elastic modulus using micromechanics and genetic algorithm. Here is the outline, introduction and micromechanics modeling, model validation, genetic algorithm, and result and conclusion. So far, most of the research on optimization of fiber reinforced composites focused on laminated structure composites consisting of a unidirectional fiber composite for each layer. And also, most of the researches on woven fabric composites are developing micromechanics model to predict the mechanical properties of the composite. So we thought it is necessary to do research on structure optimization for woven fabric composite because we still don't have much research result on structure optimization of woven fabric composite. So basically, we try to do two things through this research. First of all, we try to optimize the structure of a woven fabric composite, and also we try to analyze the mechanism between the optimized composite structure and mechanical properties of the composite. So for optimization process, we try to improve the mechanical properties of the composite. And we use the micromechanics model for woven composite and the genetic algorithm for optimization process. Here is a plain woven structure. It has a field strand and web strand and matrix. Woven structure composites are consist of repeating unit cells. This drawing is the cross-section of AA line, and this drawing is cross-section of a BB line. We build woven fabric, geometry of woven fabric using these equations: upper axis angle, neutral line, thickness, something like that. These are the equations for fiber volume fraction of a woven fabric composite. You can get the elastic properties from stiffness matrix of woven fabric composite, like Youngsan modulus, Poisson's ratio, and shear modulus. To obtain stiffness matrix for woven composite, you have to calculate stiffness matrix of UD fiber composite first. That's for strands. And then you convert the stiffness matrix into global coordinate system. Then you can get the stiffness matrix of an element, like this kind of element. After that, you can get stiffness matrix of a woven fabric composite. Then you can have elastic properties from this stiffness matrix. Before we do the simulation, we did some model validation. So we compared our model result with result from reference here, and then the result both results looks agrees very well, even though some difference here at higher volume fraction easily see, but generally it agrees very well. And this one is the material property that we used for model validation, and that comes from this reference. Okay, genetic algorithm. Basically, we try to maximize the elastic modulus, and this one is the chromosome string HWHF, AWAF. So HW is that thickness of a web strand and thickness of field strand, and the width of web strand and width of field strand. So first of all, we generated 20 random chromosome strings. With this string, we generated the geometry of woven fabric, and then we obtained the elastic modulus of the composite, and then we compared the best chromosome with the previous best chromosome. So if the current chromosome is better than the previous one, then it will be changed. But otherwise, we keep the previous chromosome, previous best chromosome, and then we did a crossover and replaced with the worst string with the new random string. In the genetic algorithm, typically they used a mutation process, but we didn't use a mutation process. Instead, we used some kind of a replacement process, which is the worst string was replaced with the new random string. Random string means that the component of the strings are random numbers. So if the best string is not changed for 100 times, then the algorithm will be finished. Okay, we set up 5 search area cases, from case 1 to case 5. For case 1, all the variables are in between 0.5 to 3. So HW is 0.5 to 3, and HF, AW, and AF also. In case 2, we fixed the thickness of field and web strand, and then we changed the width of the field strand and web strand. In case 3, we fixed the width of field strand and web strand, and then we changed we searched some optimized values of thickness of web strand and thickness of field strand. In case 4, we fixed the cross section of a web strand. So the thickness of web strand and width of web strands are fixed, and thickness of field strand and thickness of width of field strand will be optimized. For case 5, HW and HF are dependent on each other, and AW and AF are dependent to each other. So both HW and HF, both thicknesses are in between 0.1 and 1.4. AW and AF, the widest variables are in between 0.1 and 2.9. Okay, we try to maximize the elastic modulus, like I said in the previous slide. We set up elastic modulus E11, E22, E33, and E11 and E22, and E11 plus E33, E11 plus E22 plus E33. So here there are some plus signs here. Plus sign means that summation with equal priority. Okay, this one is that GA convergence examples for E11 in case 1. We used plane woven composites, like I mentioned in the previous slide, and the constituent materials are glass fiber and epoxy resin. And we set fiber volume fraction of woven fabric composite 0.4. The reason why we set the fiber volume fraction 0.4 is that we try to simulate with some kind of representative volume fraction, because we try to avoid a lot of redundant research work. So we searched some literature, and based on the literature review, we saw the 0.4 is the reasonable values for our representative volume fraction. Okay, these are the results of case 1. Strands are kind of unidirectional composites. So the longitudinal properties, longitudinal elastic modulus of the strand was significantly higher than the transverse elastic modulus. So for E11, the direction of E11 is along with the x1 axis, so this direction. So to improve this direction, you better have large volumes of field strand because the fiber of a field strand are aligned along this direction. So that it's better to have large volumes of field strand. And also, you don't want to have large waviness, because if you have large waviness with the field strand, then that will reduce the E11, the values of E11. So you better have a small waviness of field strand, so that you can have this structure of a field strand. For web strand, the fiber are aligned along this direction, so that this one is the transverse direction of the E11 direction. So it's better to have small volumes of field strand, web strand to increase the E11 in unit volume, so that you have this kind of structure. So the total structure will be like this. For E22 direction is this direction along X2 axis. So you need to have large volumes of web strand with a small waviness. However, if you increase the stiffness matrix along G axis, like or X3 axis or out of plane direction, then you need to have a large waviness, so that the fibers are aligned along out of plane direction. So to obtain large waviness, you better have a large thickness and a small width. For E11 and E22 case, the optimized structure will be like some kind of flat. One thing I have to mention is that if you consider E33, E11 and E33, the structure are almost same with quite similar with the E11 case, because they are quite similar with the E11 case, because E11 is dominant to E33, because E11 is kind of longitudinal property. However, E33 is kind of transverse properties along transverse property to fiber direction. So that E11 is the dominant property. So that the structure of E11 and E33 are quite similar with the E11. For case 2, the thickness of web strand and thickness of field strand are fixed. So in this case, to increase E11, you need to have a long field strand and a short web strand. For E33, you need to have a large undulation with a small width. So if you reduce the width, then you will have a large undulation. For case 3, the width of field strand and web strand are fixed. So for E11, you need to have a thick strand, because widths are fixed. For E22, you need to have a thick web strand. For E33, you need to have a large thickness, because large thickness can increase the undulation of the composite. For E11, E22 is some kind of flat shape of composite, like I saw in the previous slide. And case 4, HW and AW are fixed, which means that the cross-section of web strands are fixed. So only field strand, the geometry of field strand will be changed. In this case, it was converged into two cases: thick and narrow field strand and thin and wide field strand, like this: thick and narrow field strand, thin and wide field strand. Okay, in case 5, HW and HF are dependent on each other, and AW and AF are dependent on each other. The reason why we did this simulation is that if the thickness and width are fixed, then what will be happen for optimized structure? We were curious about that. So in this case, generally, the optimized result of case 5 were similar to those of case 1. However, because of these dependencies, the optimized values are converged to local values in several cases. So E11, E22, you have for E11 you need to have a large volumes of field strand. For E22, large volumes of wet strand. However, other cases, the optimized structure will be divided into two categories. E11 and E22 also divided into two categories, and E11 and E22 E33 also divided into two categories. Okay, here is the conclusion. We did some structure optimization of woven fabric composites to improve elastic modulus. To do that, we used the micromechanics for woven fabric composite and genetic algorithm for optimization process. The fiber strand in woven fabric composite is kind of unitary composite, so that they have a high longitudinal elastic modulus and a low transverse elastic modulus. So to increase in-plane elastic modulus, it is better to have a large volumes of related strand. For example, large volumes of field strand for E11 and large volumes of web strand for E22. For waveness, it's better to have a small waveness for E11 in-plane elastic modulus like E11 and E22. And the large waveness for outer plane elastic modulus like E33. Due to the dominance of E11, the result structure for E11 plus E33 were quite similar to those for E11. The optimized structure for E11 and E22 was thin and wide, resulting in high in-plane elastic modulus. Because of the interdependencies of HW and HF and AW and AF in case 5, the optimized value were converted into local values in several cases. All of this work are published in Composite and Advanced Materials. Okay, thank you for listening.